Well, hi guys. We're going to start on second day of our 8-1 notes. If you remember yesterday, we introduced binomial distributions. And still, before you do any of the work I'm going to show you today, remember you must prove that it's binomial by following BINS. Any problem you do, you need to do BINS, binomial independent fixed number and same probability. So just a reminder that that's what we did yesterday. Let's see if I can get the next slide to progress here. And I cannot. There we go. So what I want to do today, because you did all that binomial work in your homework last night by hand using the formula, but really the best way to do this is with your calculator. As I've told you before, you must know the meaning behind what you're putting in the calculator, and that's what yesterday was all about. So let me show you now the calculator functions. So recall that we have the notation B means binomial situation, and then we have N and P, the number in our situation, and the probability of success. So if we're going to say, here's our distribution, find the probability of no more than one success. Okay, no more than one means none or one, right? Just as we've been doing like in last chapter 2. Chapter 7, the probability that our random variable is less than or equal to 1 is that x is 0 plus that x is 1. Okay, and so this is what you did in your homework last night. You did those by hand. But going to the calculator, you would write out the command, which is in your TI 83s, 84s, binom PDF, and then it's NPX. So I kind of remember this is that it does go alphabetical, which is cool, but your number of objects that you're in your set, your probability of success, and then X is the number you're looking for, zero, like up above 0 or 1. And PDF stands for probability distribution function. We've been creating those in tables in chapter 7 and still now. So this is your probability distribution function, but it's binomial. So this is the command. Now on your papers, whenever you are using the calculator to do this work, you must write down the entire command with the numbers in the parentheses that you're using. That's required by AP Stats, and that's a College Board on the test, and it's required by me. Okay, so if you go to your calculators, which I hope you have with you, if not, pause this video and get it out. Okay, you're going to go to your second bars, which is distributions, because we're doing a probability distribution. And option 0, if you have a different calculator, look for your binom PDF function. And in this case, our N is 10, and our probability of success is 0.1, and we want the probability of 0, so we'd put a 0 there. Binom PDF for 0. And then you just hit enter, and guess what? You'll get that. Do the same thing for 1, just replacing the zeros with 1s, and you'd get the probability that x equals 1. And of course, to finalize for this problem, then we would add those two together. And remember, you're always putting your answers in context. We had to talk about that even last chapter. This would be a 73 point, oops, Miss Straub has a boo-boo there. That should say 61% chance of getting no more than one success. Okay. Now, if you wanted to, you will be asked to create a chart that shows the probability distribution for each X, like we were creating in last chapter. So I'm going to go through this. This is pretty cool. The example we've been using is 4 coin flips, and the random variable X will be the number of heads you get. Okay. So here's our table. We've been used to seeing this one. You can get from 0 to 4 heads, and here's how the distribution goes, right? But in order to fill this table in now, instead of running through all the other formula, you could just go to your calculator. What is our N now? Our N is 4. If I can get up here, right? We're doing 4 coin flips. So N is 4. You are doing probability of success. We're assuming it's a fair coin is 0.5. And then that you get 0 heads. Okay, so of course we can go on here. And each one would be then that it's 1, 2, 3, or 4 if I move me down just a bit. Okay. All right. So here's what's really cool that I was talking about earlier. You can use binom PDF command, put in here your N, your P, and then you could tell it to take the numbers from list 1. So if you go to your list 1 and put in 0, 1, 2, 3, 4, then it'll run this binom PF. You don't have to do it each time. You could do one straight command after you have all your X values in list 1. Run that binom PDF, and voila, the entire table shows up in list 2. You'll get the entire distribution table in one swoop command. So I highly recommend this command to you as well. All right, now what we were just talking about was PDF, probability distribution, where it's for each value of X, but you also are going to sometimes want to look at a CDF, cumulative. We know what cumulative means. It's like everything up to that point. Okay, so it's going to be a chart just like the PDF chart, except for now it will show cumulative values. And of course, our very, very last entry will always be 100% probability that it happens, at least that there's no more than 4, right? Can happen. That's 100% chance that you get no more than 4 heads out of 4 tosses. So here's our probability of 0. That didn't change because that's the only one in the chart. But you will notice that this probability for 1 is now the probability of 0 plus the probability of 1 up to that point, cumulative to that point. So likewise, I just moved down here. This number, 0.9375, is 0 plus 1 plus 2 plus 3, cumulative to that point. And it kind of reminds us, remember that cumulative, the ogive we did that showed the cumulative graph getting close to 100%. So we have seen this before in an earlier chapter. And then as always, your last option should be a 1. Okay. So how do I do this lovely thing in our calculator? And I highly recommend, once you've proven that your probability situation is binomial by using bins, I'm going to repeat that again. You must write out bins and show your reader that you have proven it's binomial. Then by all means use these calculator commands. Much faster, much more accurate. So you have your second vars, or I should say less chance for mistakes, right? That's how you can be more accurate. So again, you go to your distribution, but this time instead of binom PDF, you go to binom CDF, okay? And it's still NPX like we had before. Here's where that list comes way in handy. Again, put your X's in L1. Okay, 0 through 4, like here, whatever yours are in the context. And this time we hit binom CDF. 4 is the number in our 0 to 4 heads possible. Okay, 0.5 is the probability of success, and then take list 1 and dump it into L2, and you will get all of these cumulative probabilities. Boom, 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 there. Now, the nice thing with this video is you could pause this right now, and you can enter these things in your calculator and make sure you understand both how to do binom PDF and binom CDF before we move on. Okay. And by the way, I just equated there, forgot about this little command that I added right here to show you that instead of doing 0 plus 1 plus 2 plus 3, you can go to your calculator and do binom CDF of 4 with probability 0.5 up to 3. So remember, when it's CDF, this would be adding everything below it and including 3. Okay, includes 3. All right. What about finding the mean and the standard deviation? Remember, another word for mean is expected value, the expected value. So now that we're doing binomial, okay, these are pretty easy. The expected value for binomial only, okay, this is not for all sets, only if you've proven bins, then the mean is NP. And then your standard deviation over there is NP times 1 minus P square rooted. Your variance would be without the square root, of course. Warning, warning, only good for binomial distributions. Another lovely thing for me to tell you is that these two formulae can be found on your formula sheet that you get to use on the test. And it says a binomial distribution heading, and underneath that heading, it shows you these two formula. So if you get caught up in it or forget it down the road, there it is. You can always find it there. So we're going to stop right here for a moment, and you should have a worksheet from your sub. And I want you to go to the first page. Excuse me for a moment. I'm going to get out of this if this will let me. Oh, I need to check it here. Don't you like that I'm not having to stop every 5 minutes right now? And you have a worksheet that, oops, there we go. Well, let me scroll it. I'll scroll it this way. There we go. This one right here. So what I'd like you to do right now is I want you to apply this binomial situation. Read this problem that you have, describe if it is binomial random variable or not, and then scroll down here. I'm going to scroll down. There's the mean and the standard deviation. Use those two new formula that I just gave you, NP and a square root of NP times 1 minus P. And when it says interpret each in context, tell me what the mean is in context of this COLA problem and what does it mean about the standard deviation. Okay. And then it says of the 30 volunteers, 23 made correct identifications. Will that give you convincing evidence that the volunteer can taste the evidence between the diet and the COLA? So right now, stop the video, answer those questions, and then come back when you're done. There's your formula back up there in case you need to see it. Okay. Now that we know how to find the mean and the standard deviation, what is nice is that we can then do some other work with this. So I have in your Google Classroom a demonstration applet that I want you to go and play with. I'd like for you to change the n first, like leave probability where it is and change the n and see what happens as n increases. And then I'd like you to change the probability and see what happens as the probability gets less, closer to 0, as the probability gets greater, closer to 1. What happens to the shape? So go play with that for a little bit and then come back here. Don't spend a long time. Just go for a little bit and see what it's like. Okay, welcome back after playing around with that app. Your worksheet shows you some things about what would happen in this situation. So you notice it starts off with probability as 0.8 on the worksheet, and then just a small number of trials, 10. And we can see the data is skewed left. Sort of normal-ish, but got quite a bit of problems. As n increases, we went to n being 20, 30, 50. What is happening to that? You should have noticed that it's still sort of skewed left because the tail, there's a teeny tiny tail that goes along here. So it's still skewed left. However, it is definitely more and more normal. So we can use a normal approximation when n is large. And just how large is n? Well, we're going to learn that later on, but in a big theorem. We'll be talking about that soon. But anyhow, as you can see it, there it goes bigger. Now, the next two slides on your paper show what happens when n is 0.5, even though when probability is 0.5, even though n is small, definitely normal. There's no skewedness. It is a normal distribution, fairly normal distribution. And of course, what happens in the next slide is showing, what happens when the probability is getting closer to 0? Now the probability is 35%. You could see that when we go below 0.5, we get skewed right. There's a little bit of tail there. Our N is 30. That's the magic number, actually. And we can see that it is fairly normal, but it's still skewed right when we go in that direction with our probability. Okay, so let's go back to our slides and summarize this. Oh, Mrs. Straub messed up. Dang it. Let me escape and go back to the current slide. Sorry about that, guys. You knew I couldn't do this smoothly, huh? From current slide. There we go. Okay. So if the probability is 0.5 that you're using, at close to 0.5, you know your distribution is going, the shape is going to be just symmetrical. Based on what you just messed around with the app and saw in your worksheet, if the probability gets closer to 0, then the data set is skewed right. If it gets close to 1, and then it is skewed left. This is a great slide to remember, but hopefully you'll visually see those graphs in that applet that you looked at. So why is this a good thing? Well, because we can also do a normal approximation of our binomial distribution. Now, let me emphasize this. The binomial distribution formula, that gets you exact, but the normal approximation will get you close. How does this help? Well, this helps when n is large, we can use a normal distribution. Okay, and when n is large, we don't want to be calculating all those individual p-values. That's kind of tedious at times. Of course, the calculator would do a great job calculating these now. Okay, so either one, but just to get a normal approximation. Okay, but I cannot use normal approximation unless I check these two conditions. Please jot these down. You must do these. U times n times p and n times 1 minus p. So if the probability is 30%, 1 minus p is 70%, right? You multiply those together, and both must be greater than or equal to 10 in order to use the test. So now we're running our normal set using the NP as our, remember that's the mean of binomial, that expected value we saw in the earlier slide. And then NP times the square root of 1 minus p is the square root of that is the standard deviation. So we're going to use that. Now you can go find z-scores. So let's do an example. So here's your n is 2,500. Your probability of, your standard deviation. No, I lied. What is that? Standard deviation. No, this is binomial, not normal. Sorry. Your n is 2,500. Your p is 0.6. So NP is your mean there. And when you times those together, it's greater than 10. There's n times 1 minus p, which would be times 0.4. And that is greater than 10 also. And there I calculated for you the standard deviation of n times p times 1 minus p, square root it, and you get 24.49. So now we can go to a normal distribution that has our mean of 1,500, which is that NP right there, and your standard deviation. If we want to know what's the probability that you get greater than 1520, then you just plug in 1520 for your x value in z. Remember, it's x minus mean divided by standard deviation. Okay, I got a z value of 0.82. Looked that up in the table and get 0.7939. But because I'm going greater than, I need to do 1 minus that. So my answer would be there's a 20.61% chance that I would get greater than 1520 in context, whatever that context is. So what I want you to do next, well, we'll do binomial practice, and then you can do your binomial practice to finish on your worksheet. So let's hear, we have 700 graduates from MVHS. That's a lot. We don't have that many this year. And we use, traditionally 40% go on to graduate college. So what's the probability that more than 300 of our graduates would go on to college and graduate? Is this binomial? Okay, remember, think right now, think of your bins. Is it binomial? Is it a yes-no situation? Okay. It's either they graduate from college or they don't, right? Are each one independent? Well, we'll have to write down on our paper, assume independence, assume that each college graduate is independent, or each MBHS student, I should say, graduate is independent of each other. N, there's a fixed number. And S, they all have the same probability of 40%. So yes, we've got binomial. So then we have to say, okay, now can I use normal distribution? This is sounding like a lot, I know, but you cannot use binomial distribution unless you prove bins, and you cannot use normal distribution unless you prove that it's fairly normal. So you check for NP, and N times 1 minus P, and I'm in the way again. Okay. And both of those were clearly greater than 10, so we can go ahead and use normal. So I'm going to calculate my z-score with my new mean of NP and my new standard deviation, about very close to 13 when you round it. So there's your x minus mean divided by standard deviation. That goes to 0.9382, but because I wanted 300 or more, that's going to the right, so I need to subtract that from 1. And I get a 6.18% chance. Okay? And remember, then your final step will be to write that in context. You please change your decimal to a percent and then put it in context. Compare this to the binomial PDF that we would have done with the calculator, or here's the formula. Yikes, move this again. I keep getting in the way, don't I? All right, so there's your NK, now your combinations that you need to put in. 0.4 raised to the 300 and times 0.6 raised to the 400. Okay, or as I've told you now, it's a lot easier to use binomial CDF. So we had 700 is our N, 0.4 success, and 300 is our X, and we get 0.9427. So again, when you subtract that from 1, you get a 5.73. So as you can tell, they're not exactly the same, but remember, this is accurate. This one, the normal, is an approximation. But on the same side, they're only 0.0045 off. I mean, just less than 0.5% of a difference. So when you need an estimate, the normal distribution is a good estimate. If you need to be exact, then you must use binomial PDF. Okay. And then I just put in here a reminder that you can do your combinations if you're doing this formula in your calculator using the NCR command. If you go to math, probability, and then choose the NCR, but what you have to do first is you have to enter your N before you do that. So like if you had 700, choose 300, you have to enter 700. Then go to the math probability and enter the NCR command. And then enter the R of 300 here. And then hit enter, and it would tell you that big number that goes right there of 700. Choose 300. So here's another calculator command for you. All right, before I go on, I'm going to go back to our worksheet. And now you're going to finish the last page, which will be a practice of a normal approximation with an additional problem here about the number of teens who use a debit card. So it asks you to check the conditions for normal. So that's where you do your NP and your N times 1 minus P. And then you use the normal distribution to estimate that. Try that example, and your sub can show you my answer key. And then you're done for the day. I hope that this is making sense, and I miss you guys today, but I will see you on Monday. I'll see you back tomorrow on some more notes. Okay. Now I just have to figure out how to shut this off. There we go. Bye.